Good evening. Thank you for joining us this evening for a Currents lecture. As you know, Currents is a multi-purpose series. It's a platform for a variety of things, including an opportunity to showcase our visiting professors. And this is the case tonight. Our guest is actually teaching one of the upper level studios with students working on a high-rise building with sustainable design principles. Anyway, I'm delighted to introduce Dirk Henning Braun, the university professor at RWTH Aachen University and holder of the chair of building technology. He's also a practicing architect who worked with Norman Foster before leading his own office that specializes in sustainable design. This office, BRAUNARCHITEKTUR, works on challenges in science, research, and practice, and is a contributor to various interdisciplinary award-winning projects in Germany, the UK, the US, and Australia. The studio tackles projects at all scales, aiming for the optimal integration of structure, advanced building technology, and renewable energy systems. As a professor of building technology, Professor Braun has an extensive record in managing large interdisciplinary teams to implement research and development projects, as well as in initiating and leading a variety of startups and spin-offs. Professor Braun is active in various honorary functions and served until 2020 on the board of the VDI, Society of Construction and Building Technology in Germany. Please join me in welcoming Dirk Braun.
Thank you.
Thank you for giving me such a warm welcome here in Miami. My name is Dirk Braun. I'm a professor, architect, and researcher, and head of the Building Technology Department at the RWTH University in Aachen, Germany. In Aachen, I work on globally relevant research questions in the field of sustainable architecture and energy-efficient building systems. My architectural studio, BRAUNARCHITEKTUR, incorporates such scientific investigations into real buildings under real conditions, adding to the built environment our project with simulations running for years. We call our method zero-emission building design. In the next couple of minutes, I will familiarize you with my work in 4 sections. I will talk about climate change and its consequences for us architects and designers, give you insights into my personal journey in architecture, explain the principles behind our design approach, what our studio has been able to accomplish, and finally, provide you with some perspectives on future challenges, both in research and practice. By now, there's a little doubt. CO2 emissions caused by humans are heating up the planet. This makes the Earth getting steadily warmer, leading to further danger. Tipping elements of the Earth system could become unbalanced. These are rainforests, ocean currents, or ice sheets. If they cross a certain tipping point, according to theory, these systems may be irreversibly destroyed with catastrophic consequences. If one tipping element falls, it threatens to affect others in the Earth system, leading to a chain reaction that could push the planet towards a new hot age. Researchers at the Potsdam Institute for Climate Research, PIC, have identified some of these jeopardized tipping elements, among them Earth's large ice masses. When global warming causes the ice at the poles to melt, the darker ground underneath will be uncovered. This surface, however, absorbs more heat, which further accelerates the melting process. The Arctic Sea ice is an example of its kind of tipping element. It has been retreating since years. Due to the feedback effect mentioned above, the region is warming twice as fast as the global average. By the end of the century, the Arctic Ocean could be ice-free in summer. Even the massive ice sheets on the world's largest island, Greenland, is melting. Recently, at an ever-increasing rate. This means that the ice sheet, which can be up to 3 kilometers thick, loses more and more of its height, which increasingly exposes its surface to warmer air layers and thereby reinforces the melting process. Scientists fear that if anthropogenic emissions continue, the Greenland ice sheet may collapse completely by the end of the millennium. This alone will raise the sea level by 7 meters. In the southern hemisphere, there are even bigger ice masses in Antarctica. Scientists are already seeing evidence of the beginning collapse of the western ice sheet. Over several centuries, this could raise sea levels an additional 3 meters. The ice sheet in the east of Antarctica could also face a similar fate, but so far this region has remained surprisingly stable. Continuing global warming of 2 or 3 degrees Celsius above the pre-industrial levels, however, could change that. Miami's 1 million residents are living in an environment that is less than 1 meter difference in altitude from sea level. And their resilience is tested every season by increasingly severe weather events from month to month. I'm more than surprised that the people who can afford houses like this do not worry about the prospective value of their land. At least the owner on the right thought about rising up his property by 1.5 meter. The permafrost soils of the Arctic regions in Siberia and North America are also a cause for concerns for researchers. The particularly rapid warming in the region threatens to thaw them completely, releasing vast amounts of carbon dioxide and methane that are currently still stored in the frozen soils. These greenhouse gases will likely boost global warming even further. Scientists see a similar danger with methane hydrate, which is methane trapped in the ice that is bound up in ocean sediment. Large deposits are said to exist, especially in the Arctic Sea, in eastern Siberia, and they are already disintegrating because oceans are getting warmer. During this process, the short-lived but dangerous greenhouse methane escapes into the atmosphere and could cause it to heat up even more over the long span of thousands of years. In addition to ice masses, air and ocean currents are also belong to the tipping elements at risk. In particular, the Gulf Stream, an ocean current that creates the mild climate in northwestern Europe, is already measurably losing strength. This could result in sea level rise along the Atlantic coast of the US and cooling in the North Atlantic area. Other studies also identify heat waves or a decrease in summer precipitation as possible consequences. Another tipping element of this kind is the El Niño weather pattern, which occurs every 2 or 7 years. It reverses the direction of warm surface water currents in the eastern Pacific Ocean, which then suddenly flow in the opposite direction from Asia to South America. The severe consequences of El Niño could become more frequent if climate change continues unchecked. They range from heavy rainfall on the western coast in the US to dry conditions and drought in Australia and Southeast Asia. Another element that also influences the weather in Europe is the jet stream in the northern hemisphere. The wavy band of strong winds separates the cold air masses of the Arctic from the warmer temperature region further south. Climate change appears to already be slowing the movement of jet stream waves around the Earth. The result? Large-scale weather conditions that persist for weeks, which can also lead to extreme weather events such as cold and heat waves, droughts and floods, such as in the summer of 2021 near Cologne. So the visible results are not away from home. They happen just now and right in front of our door. Air currents in other regions in the world may also become destabilized. The Indian monsoon, for example, is responsible for 90% of rainfall on the subcontinent, but could become unstable due to climate change, resulting in alternating floods and extreme droughts. The monsoon in West Africa, on the other hand, could slow down because of climate change in such a way that the Sahara suddenly see more rainfall. The desert could turn green. But this would also have negative consequences. The life-giving source of desert dust, which is carried away by winds and supplies even the Caribbean with nutrients, could dry up. The decline of the Amazon rainforest, on the other hand, could impact the Earth's climate as a whole. Researchers fear that climate change combined with deforestation and fires will cause the enormous ecosystem to collapse. The consequences would be impossible to predict. The transformation of the forest into a dry savanna would wipe out once massive carbon sink that binds CO2 from the air. The rainforest already emits more CO2 than it absorbs, thereby contributing to climate change. They account for 1/3 of the world's forest cover, but face tremendous pressures from pests, fires, and water shortages, all of which are being exacerbated by climate change. Crossing the tipping point would mean that these forests could be displaced by shrub and grasslands. The ocean also harbors ecosystems considered to be tipping elements, the coral reefs. These fragile habitats are damaged by even slight temperature changes and the acidification of the oceans. The so-called question can be the result. Scientists expect that most of the reefs will be lost even if warmer can be limited to a maximum of 2 degrees Celsius. Another tipping element in the ocean is the marine carbon pump. The ocean absorbs massive amounts of CO2, about 40% of anthropogenic emissions to date. Algae need the CO2 to grow, and after their death, they sink to the ocean floor where the carbon is stored. But the system could lose some of its capacity as the weather becomes warmer and more acidic. A survey from 2020 clearly shows the self-perception of various countries when asked whether climate change has a positive or negative impact on them. The results are telling. 7 out of 10 people in India suspect that climate change will clearly affect their daily routines and future. It looks similar in the Philippines, a country that repeatedly suffers from severe weather events. I was surprised by the results from Spain, where only 1 in 3 foresees a change in their living conditions due to climate change. This is particularly odd because in 2003, the hottest summer in Europe in the last 50 years, around 35,000 people died of overheating in Spain. On the other hand, the survey results from the US are not surprising. Only 1 in 2 sees climate change having an impact on their living environment. This is worrisome because this means that the most powerful country on Earth and one of the largest emitters of CO2 still simply doesn't know enough about the consequences of climate change. It's also interesting who is being held responsible for climate change. A survey from 2019 describes that in Germany 1 in 2 people believe that climate change is a man-made, while around 5% suspected other reasons and only 2% believe that it's all nonsense. This fraction, who are called Querdenker, could be translated with lateral thinkers in Germany, should not be underestimated, because people can be radicalized quickly in an environment of various conspiracy theories. In Australia, it looks similar, with those rejecting theories on climate change already at 5%. In the US, almost 20% are unwilling to take the results of climate change into account. One should not underestimate this breeding ground for all kinds of alternative scenarios. There needs to be an ongoing clarification with examples from daily experience, supported by transparent reporting and credibility from scientific findings. This 2020 survey makes another issue evident. Who are the key players from the point of view of the respondents? And who has the greatest leverage to take charge of things and change them? As expected, only 15% in China believe that each can make their own contribution. 90% see national and international authorities as having responsibility. In South Korea, it looks a little bit different. Here, 35% feel caught up upon to contribute to overcoming the crisis. In my homeland, Germany, 1 person in 2 assumes that they can contribute something positive to climate change through their own personal behavior. In the US, more individuals trust themselves to change the situation, and only 60 to 65% believe that authorities will make the right decisions. One could always use that to build a strategy to lead to approximately 300 million Americans to take their own initiative. Finally, there's an interesting temporal development in regards to the question, shall we continue as before? Will there really be dramatic change, or is it all too late? In India, there's been a slight degree of frustration over the past few years, with a proportion of respondents who are of the opinion that the situation is beyond saving, rising from 9 to 22% over 3 years. This shows that one can get the feeling to not do enough about weather change. The answer to these questions from Russia are frightening. Here, almost every other respondent is of the opinion that business as usual is perhaps the best for them, and this tendency is increasing. Practically nobody believes in change, only 1 in 3. In North American countries, there is a positive trend because business as usual has changed significantly in the last 3 years, decreasing by 15 points from a starting value of 31. Also, a belief in possible influence through change is evident because only 11% believe that nothing can be done in any case. This is certainly related to the fact that the percentage of those who perceive drastic changes has increased by 12% from 39 to 51. The crucial question for us architects, designers, and engineers is so obvious that I sometimes wonder about how seldom we talk about it, especially among colleagues within the university less than outside of the university, or in the real world, as I sometimes like to describe it. In my opinion, this conversation takes place in part or not at all. We have an enormous responsibility and a very broad sphere of influence in which to make a decisive contribution to reducing global warming. Because everything we conceive and plan will influence the built environment for a very long time. That means everything we conceive today must still function acceptably and sustainably in 50 or 100 years or even longer. Our sphere of activity extends to each of the 3 most important emitters of CO2 in modern industrialized countries. About 44% of the emissions are caused by industry, 33% are caused by manufacturing sectors, and about 22% by transport. These are all areas in which architects, designers, and engineers work, and can be shaped with the help of our professions. Our sphere of activity is very diverse. Therefore, we can always help to shape 35% of the processes in the most influential area of industry. In other words, we can influence locations, conversions, expansions, or desensifications of industrial plants. We have also very high influence in the transport sector because buildings such as airports, train stations, or even just pickup locations for e-bikes are tasked to be planned and designed in the midst of the lived-in and built-up environment. Unfortunately, I must admit that it looks bad when design architects have little to say on these matters when planning production sites. In the area of residential construction too, we aren't as well positioned as we think, because only 55% of the construction volume that is put around just in front of our noses in an urban context has been planned and built with architects. The industry for finished buildings traditionally avoids the use of highly creative architects and thus avoids a greater influence on our areas of activity. So we have to work on that. My life as an architect, and I mean as a real architect, not a student, started in 1998, shortly before my graduation, when I was scouted practically mid-presentation within 2 weeks from Ingenhoven, Düsseldorf, Renzo Piano of Genoa, and Foster & Partners from London. My wife picked London. We had 2 kids and no idea what to expect. Suddenly I was sitting on the world's poker table of architecture, and the first weeks with Foster made a tremendous impression on me. It was a normal occurrence at the office to run on one day into Vivienne Westwood, or on another day Gaddafi's sons inquiring a new airport or an entire new city. Possibly because I was a German architect from a historical background that involved Hitler and Albert Speer, I was rather concerned about requests like this, and I learned quickly that the English, undefeated on European battlefields over the last 800 years, had a rather different attitude when it came to realizing even somewhat questionable projects all around the world. But the fact was that I was on the Champions League of Architects, which was exactly where I wanted to be. To me, the Reichstag in Berlin or the headquarters of the Görling Insurance Company in the middle of Cologne meant valuable experience in how a globally active architectural firm implements its design philosophy at the highest level, from the planning phase to physical models or to the real building. Before Norman sold large chunks of it to 3M and other investors, that was the firm's defining aspiration. Having Ron Dennis on the team, the CEO of McLaren at that time, when designing the McLaren headquarters and especially aiding the team by applying my 3D skills to the design of the roof structure, was an inconceivable valuable experience for me as a young architect. Only few people know that their designer active at the time, Adrian Newey, who now works for Red Bull, created full-size analog drawings of all of the Formula One cars on a 20 by 13-foot whiteboard sitting in a chair suspended from the ceiling. When Newey left for the day, his designs were digitized and then immediately baked into physical form in an autoclave by means of carbon lamination in the space of a few hours, so they would be ready for him in the morning. My final project with Foster was the 126 Phillip Street high-rise in Sydney, Australia. To be honest, I was somewhat shocked at the fact that a leading firm like Foster would show so little ambition in persuading the client, Deutsche Bank Australia, a subsidiary of Deutsche Bank in Germany, to use energetically optimized methods. My decision to eventually leave Foster to make it on my own was certainly inspired by the following statements of my partner in charge. Imagine intending to keep a milk carton at 8 degrees Celsius, placing it in the Sydney high-rise, in the Sydney, Australia sun, and then removing any kind of insulation. And we still expect to have a milk carton that is 8 degrees cold. So that means to achieve something which is absolutely not sustainable. That was shocking me at that time. So back to Germany, we were able, in a variety of teams, to plan and build rather remarkable projects from 2005 onward. Not a small achievement, too, as a rendering architectural structures and actually building them are 2 different pairs of boots, as we say in Germany. The fully steel Astor administration building won 4 awards, and the multi-generational home found its way into 16 publications, which was not a small feat at that time. Despite being two very different use cases, both projects went without external energy sources like gas or oil. Both employ geothermal heat or deep groundwater for generating heat and cold. Electricity is sourced from PV elements integrated into the facade and used for the buildings themselves, with any surplus fed into the grid. Another important project involves 43 apartments in the middle of Stuttgart. Actually, there was no other project in all of Europe with comparable energy efficiency in 2008. With it, we set new standards for energy usage that stand to this day. The entire building's primary energy demand was a mere 65 kilowatt, which converts to about 2 kilowatt per unit, with units averaging 915 square feet. A normal building from that time would have required about 280 kilowatt and meant enormous utility costs for the owner or tenants. In the case of this concept, however, costs for heat and electricity were eliminated, and the investor was able to increase rental revenue from €1 to €1.4 per square foot. HS17 is a minimalistic single-family home that costs less than €500,000 to build and offers space for a family of 4 and 2 integrated rooms for students. To deliver a home for a Mercedes-Benz engine design manager certainly is no simple task. As architects, we often marvel at cars' panel gaps as well as the perfect build quality of single components and entire model series. The MEW5 building is an attempt to achieve the same perfection and boasts intricate facade details in metal, wood, and glass. Also, a Mercedes R107 convertible, it's an oldtimer, serves as the background of the entrance area, framed behind glass, resembling a three-dimensional painting. MEW5 makes no use of fossil fuels, generating heat by means of a heat pump connected to a geothermal field with 4 boreholes of 90 meters. We will be looking at Villa D1 in Düsseldorf in more detail in a little while. So there are other two quite extraordinary. Villa D2 and Villa D3 are almost ready. Villa D2 is a hyper-modern villa with around 2,000 square meter space for living and working. It's including a garage for 16 cars, a huge pool and spa area, and a working unit, as well as a separated house for the housekeeper. This is finished in 2021 and will be shown in the chapter of projects. Villa D3 is also in Düsseldorf, not far away from the others. Are 3 buildings on a countryside landscape with a car house, a living home, and a training hub for the triathlon client. The make home was commissioned by the city of Aachen and was built together with the students from the RWTH and the mayor at that time, Mr. Philipp, who ordered around 300 buildings like them from us to provide shelter for refugees arriving 2015 under the auspices of Angela Merkel. That's our chancellor. However, after Merkel's deal with Turkish President Erdogan, which I do not support, in 2016, there was suddenly no need for the highly efficiently modular building elements because the refugees could be located inside Turkey without transporting them to Germany. The project still led to a patent for a segmented building elements which have been exploited yet commercially. The REALLAB in Aachen, I will be shown later in detail, That's our research building. The Stuttgart Alp Forum is an ongoing project which will be finished 2024. It's a refurbishment of a roundabout 30,000 square meter large property on the entrance of Stuttgart, which was made in the 1980s and has to restyled for the next 50 years, especially regarding sustainable use of the building. The MEDICENTER in Udem, which you can see below, is just finished, and I will show this in more detail later. The Villa D number 4 is a beautiful home for one of the steel tycoons inside the western part of Germany, and it's located on a beautiful site nearby Düsseldorf. And it took us 7 years for planning and building. It's a very complicated refurbishment of a countryside villa, which is now turned into a hyper-modern one. The Remise in Udem is an ongoing project. It's a conversion of an old remise from the 18th century to become a home for a family with 2 kids. The upcoming project is a research center in the eastern part of Germany. We are just in negotiations with the client, who will see what happens. Hopefully, this will find a good solution for all of us. To explain why the buildings we develop in the studio will be the way they are, you need an attitude, a design philosophy, an architectural position, so to speak. I want to outline them as follows. For me, a beauty or a perfect figure is created through coherent basic forms which evolve into a larger form when they are added and increased but do not lose their origins in the process. Similarly, with this magnificent folding, the shape of which is set on its own by gravity and the properties of the materials. For me, geometric order is the key property of a valid design and a guarantee for an inherent beauty, the logic of which presents itself gradually to the viewer. My doctoral thesis, Bionic Inspired Building Skins, from 2007, presents the scientific basis for understanding geometric orders in nature, which generate their natural perfection exactly on this basis. Pine cones open up on the basis of a simple and ingenious strategy of nature. Their curved geometry has a different material on the short side than on the opposite side. If the humidity of the environment changes, these two wood-like anisotropic materials expand to considerably different degrees. The cone opens and closes again with the humidity decreases. This ensures that the seed can only fall out of the cone when the humidity is so high that the seed has a chance to plant. I call that low-tech, and to be honest, that's pretty smart. The ability to adapt to changing environments, an essential property of innovative building structure, is strikingly apparent in the case of the plaice fish. The plaice is able to imitate the color and the surface of its surroundings on the seafloor, and thereby make itself as good as invisible so that hunting sea creatures cannot find it. The amazing thing about this is that the fish can capture the surface on the underside of its body, or rather on one side of its body, since it lies on its side on the bottom, and can display this result directly on the other side. an unbelievable achievement from my point of view. The placefish's attempt to camouflage itself on a chessboard, shown in the picture on the left, is almost poetic. He imitates the man-made pattern almost perfectly at the edges, and then loses precision in the center of his body. For me, it is an image of a successful failure, because he creates his own model of the game of chess. Another sea creature brings adaptive behavior to the extreme, but see for yourself and watch out, don't be frightened. So that's adaptivity. Thinking in terms of layers and strata is an essential design parameter of our work. Various functions are localized in singular tasks and, depending on the task, formed in different arrangements into a layer system. It is important to understand that over the course of a year, a season, or in a daily routine, these layers make a contribution to the interface of the thermally controlled space and the thermally uncontrolled space. We use terms such as skins, shells, sheaths, or membranes, similar to the items of clothing with which we condition our bodies for particular locations. The ability and capability of individual components of building structures depends on their integration capacity. If components can take on several tasks and thereby provide different services, other components will be relieved and can thus be designed more simply, more cheaply, or ideally with a higher quality. As can be clearly seen in the X-ray image of a spacesuit, a wide variety of tasks with various assemblies are integrated in the suit's textile cover system. Building shells should also be developed in exactly the same way, not simply being able, for example, to independently record internal and external temperatures, but to be able to react them bidirectionally. Volumes, layers or functions. For us, it is of central importance that these be permeable, be it for light, air, gases, or functional areas within a building. This also creates, almost incidentally, a diaphanous permeability, which for us brings an outstanding design component. Transitions become transparent, functions overlap, and building shells provide varied glimpses into their own worlds. Like a semi-transparent cloak, the view gives the observer the necessary space to distribute the facade of this item or clothing, or to understand what is behind it. In this way, the facade can be experienced dynamically and mystically, precisely as multi-layered as building structures are ought to be. The clients of this project had seen the multi-generation building we have built nearby Stuttgart and approaches me about it. We met up in Stuttgart at the time, and I was asked to make 5 designs, which they then wanted to look at before placing an order. This is what was handed over to the client 6 years later. The design can be best described in sections. The actual above-ground volume lies on a glass seam and is designed as a continuous volume, meaning as a large space. 2 bridge-like levels cross this room and create spaces for the children and the parents on the upper floor. The technical floor in basement is primarily designed as a counterweight for the overhang, keeping the building in balance structurally. The same longitudinal section in the middle of the building, showing the entrance under the overhang, with a direct crossing to the main floor with the living and common rooms. The underside of the ceiling extends slightly diagonally over the semi-platform staircase through the entire volume and underlies the passage through this axis. If you step up to the southern edge, you reach the approximately 15-meter wide balcony, which extends the area inside the living room by up to 9 meters. The result is an exciting spatial impression with surfaces and two-story room heights across the open overall volume. The studio and the cinema are located in the overhang. The inclination of the geometry matches one-to-one to the dimensions of the two outer flights of stairs. With this, the upper floor is opened up all around and along the visible incline, inside and outside. The silver shell encloses the volume in huge contiguous areas and gives the building a futuristic and distant appearance. The overhang here looks like a modern interpretation of a large canopy, a different way to define a classic portico. The joints of the textiles are purpose-built with 3 types of joints. The pinstripes of the textile joints inside the large pieces of the textile, then narrow joints where the textile is not stretched manually. You can see them in the image on the top nearby the sky, and maintenance joints that can be reached with a tool and 2 hands. This is where the engineering of the textile shell meets the designing architect and craft is created. The entrance is a mirrored surface made out of high-quality burglar-proof glass with an entrance door specially designed for this building, which in turn, backlight and covered flush with glass, brings its own aesthetic to this view. The ceiling underside, elaborate in profile, starts here and leads the visitor via the integrated doormat into the lower lobby with cloakroom, storage space for children things, and 2 restrooms, one for the family at the entrance and one for guests. The ground floor shows the logic of the design. On the outside, directly on the facade, there are 2 circumferential access systems, the incline of which corresponds to the incline of the overhang. This access is reserved for residents and cannot be seen from the entrance. In the middle of the building, the central, almost Baroque access axis with a lower lobby and transverse utility rooms such as a second kitchen for preparation, another restroom, the internal secondary staircase as a spiral staircase, and a storage room which was provided for later installation of an elevator. This is followed by the large living room and lounge, which extends south to the building-wide balcony. In the western part, oriented toward the evening sun, which is downside at the plan, there is a 45-centimeter sunken lounge with a 4-meter wide linear gas flame in front of a photograph of Andreas Gorski. The extremely valuable picture was removed from Daniel Hart's photo shoots for insurance reasons. In the eastern part, meaning on the morning side of the building, is the open kitchen, which was geometrically designed to handle the width of the room. In the foreground is the sunken lounge, the cushions of which are covered by Roche-Beauvoir fabrics. At the very front of the picture is a flap containing a TV that can be extended upwards. Clear, strong colors, clear geometries, and object-like items make the room appear playful and yet atmospheric. The extremely slim window profiles can be pushed aside completely into 3 middle panels, so that the approximately 4-meter wide balcony extends the living space when the outside temperature is pleasant. The lounge from the opposite direction. The fine fabrics contribute an important piece to the atmosphere of the room. The same applies to the shell armchairs from Saarinen. The black horizontal metal inlet contains the gas fireplace, a 4-meter wide, ultra-slim gas flame specially developed for this building. The black slit in the shadow joint of the Korean lounge around, which can be seen in the foreground of the picture, supplies fresh air. It was imperative to avoid the ventilation outlets being directly visible, as there are no aesthetically pleasing products of them. The illuminated door on the far right leads to the internal spiral staircase, an homage to the 19th century Wilhelminium-style buildings. There you could disappear unseen down the servants' stairs and get back upstairs. In this project, the client wanted to get into the parking garage from this area on the upper floor without disturbing the others. The hanging rod lamp was specially designed for this building and underlines the 2-story spatial impression above the sunken lounge. In this picture, you can clearly see the entire bridge-like parents spanning 15 meters across the room without any support. Above, you can see the central axis with the access of the parents' area and the atrium. The kitchen block is made out of Corian and covered in a special blue coating. All fixtures are opened electrically. The tap can be countersunk so that it does not affect the homogeneous appearance of the space. In the front right of the picture, you can see the fronts of the otherwise completely closed back wall of the kitchen, which have been pushed to the side. The niche is for morning coffee and is then simply closed again. The fronts park vertically in the side pockets. The complicated matter of lighting an open-plan kitchen, which nevertheless needs enough light on the work surface, turned out quite well. It should be between 600 and 700 lux. The linear lighting that can be seen in the picture was made in the workshop from 6 individual elements shaped into 2 6-meter-long light bodies and can be activated field by field, depending on where the light is needed along the very long kitchen. The upper floor in the plan. The central axis and the 2 external circumferential developments can be seen. Above in the plan on the east side is the client's studio. The client's cinema is orientated below on the west or evening side. The lying area is reminiscent of a boat and offers plenty of space for doing nothing on a weekend. 2 children rooms with their own bathrooms are arranged in the transition of the parents' area. You can see the continuous spiral staircase and room for a future elevator. The bridge leads to the parents' area to the south, which extends over the entire width of the building. 2 dressing rooms for him and her, as well as a bathroom with a separate toilet, provide for all of the necessary uses. In addition, a building-wide balcony under the roof overhang made out of textile. I look down into the lounge from the bridge to the parents' area. The dust-shaped lamp looks almost like a work of art. The floor below the topography of the property, a parking garage for 4 cars, the lower lobby with various functions such as storage, cold rooms, and shoe cupboards. Toward the top of the picture, a workshop for small repairs and garden tools integrated on the side to the east with direct exit to the south. Toward the bottom of the plan is the housekeeper's apartment with its own entrance from the outside and a small patio garden. At the bottom of the plan is the housekeeping area with enough space for all the needs that a building like this is bound to have. In the middle, the chorus zone in front of the 12.5-meter long pool, showers, an infrared heating cabin, a pantry kitchen, and a floor-level whirlpool offer a contemplative space, a kind of a second living room. The picture illustrates what this room was actually about. The water surface, a reflective surface, were meant to expand the large room into the third dimension and thus provide the peaceful oasis its own materiality on the floor. For this, it is crucial that the whirlpool also have the water surface all the way up to the top. This is usually not possible with hot tubs because of the bubbling water. The edge of the water is always lower than the edge of the pool. That would have seriously distorted this picture, so someone had to come up with something. To do this, the whirlpool needs a different water temperature than the pool, which is not sensible in terms of energy to maintain permanently. The idea was therefore to only heat the pool shortly before it was to be used and to lower the water in exactly that process. The client only had to initiate the process about 8 minutes in advance. I think this is an acceptable and low-tech solution. This is an image taken from around about 2 months ago and is showing that after 4 years being exposed to sunlight and rain, the silver screen still looks like from the first beginning. Each of our projects is energetically simulated before the application for planning permission and a second time before the start of the construction site. We want to know exactly which performance capabilities can be expected in the design and the conceived building technology components. To this end, we have developed 4 measurement protocols with which we can compare the simulation at a later stage during the building's operational stage. Using all the materials used in the external components, the U values of the individual areas are simulated as a proportional total U value over the entire building envelope. Then the use of renewable energies and their share in the overall energy requirement of the building, plus the energy consumption measured for 1 square meter over the course of a year, as well as the amount of CO2 saved over 1 year calculated in tons. So there you can see the simulations before evaluation of the building. There you can see the evaluation after 6 years. In this project, we were able to determine the following results using the 4 measurement protocols after 6 investigations over 6 years, meaning 1 by year, 1 every year. The U value is slightly improved, a sign of the high quality construction of the building envelope, which was constructed better than expected. The usual proportion of 10% thermal bridges could be reduced to around 3% in the calculations. The biogas feed line used as a reserve and peak load line is used less than expected, thus reducing the proportion of quasi-foil media by 5 to only 15%. In contrast, the energy consumption increases slightly by 5 points, which is mainly due to the changed user behavior. 10 more tons of CO2 could be saved due to the increased use of renewable energies. with 6 practices, 3 general practitioners, a pediatrician, a cardiologist, 2 osteopaths, and an alternative practitioner, as well as an outpatient nursing service. The new MEDICENTER in Udem offers a wide range of medical care. It's a prototype of local medical care of the future in rural areas where clinic centers are very far away. The basis of its architectural and energy plan is formed with simply and clear geometries, skeletonized construction, and sustainable untreated materials, as well as an energy concept based upon 100% renewable energies. The design is restrained, geometrically clear, and organized to be highly functional. You can see the surrounding envelope made from lightweight timber studding, the south-facing facade on the left of the drawing, and the north-facing facade on the right of the drawing are specially designed to be more closed up, while the east-facing and the west-facing facade on the top and on the bottom of the drawing dissolve towards the middle, creating entrance facades. The actual thermal boundary is located about 6.5 feet further back, forming a narrow 23-foot tall loggia space, which almost seems like a part of a house of worship, and it's a reinterpretation of a classical portico. The lobby, the 2 reception desks, each on the left and on the right in the entrance hall, is located transversely in the eastern part of the building. If you continue on a straight line from east to west, you can make out the opened exposed concrete staircase and the elevator leading to the upper floor. The physicians' treatment rooms line the outer facades, and supporting functions such as labs and storage areas are located in the building's center. On the upper floor, the floor plan follows the same principle as on the ground floor, but the medical offices here offer a shared space for staff and waiting patients. You can see this in the middle of the plan, that opens up transversely from the center of the building. You can easily make out the 2 narrow utility areas positioned orthogonally to the stairs and elevators. These areas act as a utility gallery, supplying the entire building with electricity and heat. Their central position in the building means an optimized concentration of all functions with the shortest possible supply lines. The view from the east, the 7-meter-high vertical wood steels develop out of the grid of wooden slats and alter their intervals in the direction of the central entrance in the middle of the structure. With that, 2 things happen at once. On the one hand, the visitor and patient are led to the entrance almost automatically. They understand relatively quickly in which direction they need to move. And on the other hand, the spacing of the slabs is aligned toward the sun's positions in the east, so that they provide shade to the sitting rooms in the entrance hall as a passive constructional sun shading device. The central movement area is located in the middle of the hall. Here it is lighter and less shaded than at the edges of the structure. A simple building height slat in varying depth successfully generates a peaceful and expressive facade that not only guides the visitor, but above all, furnishes an essential contribution to the structure's passive cladding. The circuit and electrical plan is intended to demonstrate the enormous planning depth available with modern CAD tools and proves that architects are back in control of planning. Even aspects of planning specifics to certain fields of expertise can be geometrically integrated and resolved by the architect before the engineer gets to work on the conceptualized dimensions at hand. The goal is to relieve the engineer of the burden of geometrical work and, at the same time, give the architect control of the typical problematic of implementation of technical features. The installation plan shown here demonstrates how the architect was able to find a solution where the individual elements work side by side without spatial conflicts, leading to a floor structure with a height of no more than 4.3 inches. Electrical cables, network cables, freshwater and wastewater pipes, feed and return lines for the heating systems, and the entire fire alarm system are organized side by side. The wooden facade was also planned in 3 dimensions with full control even of small details. The southern facade is deliberately designed to be closed off in order to prevent unnecessary heating of the structure in the summer. Here as well, the structure height slats results in a compositionally powerful facade concept because the spacing of the slabs in front of the floor-to-floor ceiling window elements is increased for ample lateral lighting. At the same time, the vertical slats provide the necessary fall prevention on the upper floor and ground floor without the need to implement a railing. The pre-grade 7 cm wide slabs are finger joined from 2 slats with lengths of 5 and 2 meters and thus connected almost invisible. An interesting fact is that the essential geometries, selection of materials and joints, are directly derived from a 3D model and only require the addition of 2D line elements and legends for a 1:10 or a 1:5 scale representation. If in this specification step it should become apparent that some distances turn out to be too small, the model can be readjusted and the spacing increased. This means bidirectional control of the architectural features. The approximately 10 cm high shadow gap is important to the design, as it enables the compact building volume to be lifted up off the natural ground in terms of its materiality. On the one hand, to support the recumbent geometry, and on the other hand, as a construction protection from splash water for the wood. During the design and installation of anisotropic materials that darken under UV exposure, it is enormously important that there is no external shading or even self-shading, because this changes the color of the wood differently in one area, a nightmare to the designer's eye. The adroit combination of ramp and entry stairs into the central entrance in the middle plays a special role. Built from large stone slabs, this entry gesture comes across as pleasantly restrained, and it does not disturb the recumbent building format. So that the parking cars do not roll up against the building, linear joints with gravel are left in the ground that cause the vehicle to stutter slightly and wake up the driver to pay attention. On the top of the sectional drawing, the vertical loggias already presented as well as the grid continues throughout the section are clearly visible. The area below the building has been prepared with a special foam glass, a material that not only provides insulation from below, but also can be used as an anti-capillary layer. The entry hall is the heart of the building and serves to reference, to inform, for waiting, and to access the upper floors. The approximately 7-meter high glass facade is triple glazed and placed 3.21 meter directly in front of the steel supports with no further vertical profiles. The horizontal partition in the middle of the grid takes the automatic sliding door up and relates geometrically to the surrounding gallery on the upper floor. Dark acoustic elements beneath the gallery provide a reduced reverberation time and complement the substantial atmosphere of this room with their foam-like materiality. You can see the building structure with forced floor slab, false ceiling and roof structure, made of recycled concrete and in situ concrete columns. The hall room is formed by 6 steel columns, the dimension of which are identical in the direction of view to the reinforced concrete columns. The stiffening walls are shifted from exposed concrete and offer space for the single in situ concrete staircase and the elevator. This creates wall-free rooms that can be allocated as flexible as possible. A few figures. Floor area, 2,300 square meter. Construction area, 300 square meter. Technical areas, 100 square meter. So it's more or less a very efficient, almost 84% of the floor slab can be used. No load-bearing facades, no wall-bearing components, thus high efficiency in the utilization of the floor slab. 3D cut of the ground floor. Recognizable are the few load-bearing components and the two inner technical surfaces, designed as two-story high technical areas. The necessary wash basin elements of the sanitary design, as well as the toilets, are supplied with water and electricity from the upper floor and drain directly down through the base plate. This allows a single tube supply system with fresh water. This saves about 150,000 euros in this project, which the circulation management and the return are not needed. An unusual concept is that we use state-of-the-art continuous flow water heaters with 11 kilowatt power to heat the hot water at the wash basin faucets. Since we do not have a traditional hot water supply for showers or bathrooms in the building, we can use a one-pipe system. This is to distribute fresh water in the building at a low cost without having to install a second hot water pipe or a third circulation pipe. This concept is initially met with resistance from plumbers who were concerned about the purity of the water during long periods of inactivity. It was possible to counter this by saying that the digitalization of electrical fittings at a fair price, less than 300 euros per piece, made it possible to have the fittings automatically flushed once a week, so that the concerns could be remediated and a modern, inexpensive system could be implemented. The conduits of the electrical and network cabling are routed on the same floor plate. It is of great importance that I am not allowed to cross any of the path, because this means increased superstructures on a few places, which lead to additional cost and a change building height. With this installation planning, the entire floor structure on the ground floor could be reduced down to 110 millimeters. Planning of the subsystem heating, ventilation, plumbing, and electrical in the superimposition with the rising walls. This is important because the walls are not yet standing during the installation of the technical fixtures, and you can give the executing company installation instructions without accidentally installing everything on site. One floor further up, the path of the freshwater supply in green and the black conduits of the electrical wiring are clearly visible. In the middle, the two ventilation controls, which can bleed all interior directly and with the shortest pipe length. This clever location of the two internal and directly connected to the roof above its two-story technical surfaces led to cost reduction of round about 400,000 euros of piping. The roof slab shows 9 skylights over the distribution and movement surfaces on the upper floor. To be recognized in blue, the roof penetrates of the pipe vents to supply and exhaust air connections of the ventilation via the two technical controls, the 5 roof drainages, and the location of the 4 emergency drainages. This planning is precisely coordinated and planned with the approximately 99 kilowatt peak PV system on the roof. This means that the skylights, the roof openings, and the air intakes and outlets must be precisely matched to the substructure of the PV elements. The panels themselves are arranged as effectively as CIS-coated modules with 330 kilowatt per module in the east-west direction as a gable roof installation. The PV system represents an important part of the total energy supply of the building. The facade plays an essential role, not only in terms of design, but above all, also energetically. The wooden frame walls, with a U value of just 0.12 watt per square meter Kelvin, which are only 220 millimeters thick, are located on the south and north facade. On the east and west facades, they dissolve into vertical slabs, which, due to their gradually installation, optimally. This is an innovative overlay of design considerations with the wood matriculation and the energetic effectiveness of the arrange. The view from the entrance of the new MEDICENTER in Udem, with the effect of the shadow gap clearly recognizable along with the extremely homogeneous transitions from the opening facade on the west and on the east to the more closed facades on the south and north sides. Here you can also see how restrained the entrance structure consisting of the ramp and staircase is. In terms of design, it belongs to the ground, not to the building, and thus elegantly retreats in favor of the design. A decisive factor for a clear design language with simple structure element is, among other things, that the upper edges of the slats are not defaced by a parapeted cover. This is achieved through a simple solution. The slats are beveled at the top at a slight angle to the rear and are pressure treated, an idea of the carpenter who carried out the work. The building shell not only insulates very well, but above all provides a structural protection from the sun that, despite the high share of daylight quality, prevents the building from warming up too much during the day and throughout the summer season due to sunlight. Direct sunlight on horizontal surfaces creates long-lasting heat storage in the bulk of the structure, and this usually has to be compensated with complex and expensive building technology systems like HVAC or other things. The lightweight facade designs are therefore serves as an external solar filter that ensures a balanced and rather diffuse illumination of the interior. The south facade is deliberately designed to be opaque and circumferentially incorporates the vertical wood steels in their fine structure and geometry. The glass facade in these designs are on the east and west facades. This constitutes another design approach from our many years of experience with large format components. The glazing available on the market today can be made with triple glazing at a fair price. This is nothing new. What is significant, however, is the choice of the spacers for the three panes and, above all, the ratio of the frame profiles to the glass surface. This is because the efficiency of panes with good multiple glazing is already at a value of just 0.5 watt per square meter Kelvin. But the frames are mostly 1.3 watt per square meter Kelvin or worse. For us, this means that the panes should be as large as possible and the frame portion as small as possible. With this, we achieve a UV value, so this is the combination out of the profiles and the panes, of around 0.6 to 0.7 watt per square meter Kelvin. This is still 5 times worse than the lightweight wall above, but it is presented as such in the overall assessment. One recognizes that is the sum of the parts that needs to be optimized, and this also applies to this project. An important property of the building shell is the insulation ability with low thermal conductive coefficient of the materials used. At the same time, the shell should also be space saving, and the surface should ideally already be treated when it is delivered to the construction site. This design logic requires a rethinking of the supporting structure, which can be clearly seen in that design. The support system dispenses with external load-bearing surfaces and is designed as a skeletonized structure in reinforced recycled concrete. This enables the exterior surfaces to be created using a lightweight construction technique that consists of over 80% insulation, and it also only has to transfer to itself its own loads as well as wind loads. Walls such as this can be much cheaper and more powerful than their load-bearing alternatives. With a system thickness of 23 centimeters, we can achieve a U value of just 0.12 watt per square meter Kelvin. These walls are not only a high-performance layer system, but also directly provide a windproof building shell that no longer needs to be treated. Due to the good building shell, the compact volume, and the clever interior layout, the heating requirements of the building is only 28.27 kilowatt. This allows the use of an extensive heat pump, the electricity consumption of which is further minimized by an upstream geothermal field with 5 boreholes of 110 meters each. The heat pump must raise the temperature by about 22 Kelvin in order to supply the transfer system to the underfloor heating with a floor temperature of around 36 Celsius degree. This small temperature rise is generated by electrical power, which in turn is kept within the building as seen below. What is special is the so-called natural cooling concept, which uses a bypass circuit to absorb the temperature level of the floor when it's warmed up in summer and store it in the ground. In this way, we regenerate the heat extraction from the geothermal field in winter with heat recovery in summer. So we recharge the soil energetically, so to speak, so that it can be efficiently available again next season in winter. Finally, a few more impressions of the interior. Here, the entrance hall from the perspective of the south reception. The wooden facade from the outside is also used inside of the outside wall and can be seen in the background of the photo. On the right, the exposed concrete stairs going up and the change of floor covering. One of the interior's access corridors on the upper floor as an example. White walls, dark stone floor, doors and acoustic panels in RAL 7021 create an elegant contrast to the treatment rooms. The glass wall on the right is located directly at the skylight and brings daylight into the rooms facing away from the facade. We architects would have liked to have ordered the sanitary items in the dark vertical slot, such as wash basins and mirrors in dark colors, but unfortunately the dark version is not available with an antibacterial coating, which of course makes sense in such a building. A small tea kitchen on the ground floor shows the alternation of exposed concrete and white, non-load-bearing partition walls. Simply furniture from IKEA, an atmospheric floor, and a coffee machine. Sometimes it just doesn't need any more. The view from the west shows the two-story building as a homogeneous volume. You can see the steel walkway behind the wooden steels, which, as the second escape routes, connects every room on the upper floor to the outside. Through its materiality, the building blends delicately into the landscape and has the appearance of a sculpture opening up towards the landscape. The simulations were the best that we could achieve so far. An average U value of 0.19 with a 500-meter glass facade would be something of a sensation. 99% use of renewable energy, an energy consumption of only 32 kilowatt hours per square meter year, and around 240 tons of CO2 savings. We are talking about a high modern all electricity building without any fossil fuels. Everything is generated, saved, and used in accordance with local requirements. That is the lived future, and I hope that these values will also be confirmed in operation over the next few years. For the testing and research of innovative building technology issues, commercial building projects for external clients are usually the wrong field of experimentation. Warranties, liability issues, and lengthy component approvals complicate developments during construction and seldom lead to the desired success. This gave rise to the idea of constructing our own test building, an experimental building, or a real laboratory. We call it REALLAB, in which virtually all questions of modern building technologies can be researched and tested without the above-mentioned conflicts. The building had to be extremely flexible in floor plan, have no fixed rooms, and be accessible and convertible in ceilings and walls at any time. Large gates with access at ground level were to ensure that even larger elements, such as technical components, could be easily moved in and out. The percentage of panes of glass should be maximized for test series with solar-controlled issues, and they should be easily accessible from the inside as well as the outside when something is changed. The building surfaces should be openly visible so that measurements and test runs can be accompanied in that area. A garden area with an outdoor pool, which should be designed, among other things, as a thermal storage facility, complements the living and working use of the REALLAB laboratory and offers space for testing cisterns, irrigation systems, and percolation techniques. The REALLAB was to be planned and built within 12 months. Costs had to remain below 650,000 euros, and the move-in was agreed by the end of 2017. The light building, which creates an almost stoic curvature, should then be covered with a magical textile cover, which should be able to change its transparency in a mystical way, as you can see in the slide. There should not be any buttons or switches. The building should think and become an automatic helper in the background during the test run. It quickly became clear that for maximum flexibility and retrofitting, only a delicate steel skeleton structure came into question. It was to be almost 100% glazed and offer external connectors, which would create a zone between the thermal cover and the building enclosure. 3 stories could be built, with 2 floors to the driveway in the east and 3 floors to the west via a modulated ramp. The basement with the large gates is thus drivable and also accessible at ground level. The entire steel structure weighs only about 24 tons and was designed to be completely free of bending moments. A comparable building made out of reinforced concrete would have a dead weight of about 420 tons and stored material, so a CO2 saving of approximately 500 tons was achieved. The building has no core. The bracing of the walls and ceiling sections is done with invisible horizontal crossings in the ceiling sections and visible vertically bracings in 3 out of 10 axes once per floor. This very soft system becomes an extremely efficient overall structure only by tensioning the tension members, similar to a violin that needs to be tuned. The steel structure was modeled by us architects in Revit 3D, down to the last screw, according to the specifications of the structural engineer, who, unfortunately, like most of them, only had an island-type structural analysis software. And so we have been able to send our drawings, not the ones from the structural engineer, directly to the steel mill's production department. So it's a logic chain from CAT to CAM without a classic paper-based shop drawing. We erected the entire steel structure on the site in just 12 days without any complications. On the way to a 100% energy self-sufficient building, a combined heat and power unit with a Stirling engine of 6 kilowatt power and a condensing boiler of 20 kilowatt power is currently being tested for heat supply, as there are also a fuel cell heating system with 1.5 kilowatt electrical and 0.8 kilowatt thermal performance. A battery storage is tested with 4.5 kilowatt, a room air system, a central vacuum cleaner unit, and a digitalized pool operation technology. 15,000 kilowatt of electricity is thus generated, which is primarily used for the building's own needs, while approximately 9,000 kilowatt of electricity is fed into the grid and monetarily effective as revenue. The entire balancing of the plant is still being tested because the gas consumption is still simply too high, so it needs to be looked into. The triple glazing with a U value of 0.65 watt per square meter Kelvin has element dimensions of 5.15 by 2.8 meters as a single piece of glass, triple glaze by the way, and a weight of approximately 1100 kilograms. Of these, 10 elements are installed on the ground floor and 10 elements on the upper floor. The system was therefore installed with an electro-hydraulic motorization for the first time and is still being tested. Motors integrated in the profile drive the large sashes and can be activated or stopped via the building control system or on the profile itself. However, time for development is still needed before the window panes work better in terms of gesture control or security features. Since the movable window panes, 5 per floor, can be opened 100%, meaning when they are fully open, there is one of the movable elements in front of the fixed partner element, which is beside the movable element. The building is almost barrier-free. You really have the feeling to be outside, although you are inside. The glazing elements are part of a research contract and will be measured until 2022. The glass house, of course, needs solar shading and prove that, even in a glass house, a certain degree of privacy can be ensured. The research project ATS, Adaptive Textile Skin, and DATEV, Demonstrate Adaptive Textile Facades, are intended to show that textile building materials, which can be individually configured in production and also have a low-cost component, almost suggest themselves to become large area homogeneous claddings for architects. This is our starting point because the REALLAB is intended to show what can be designed with these building materials. We are researching adaptive textiles that can change their opacity and transparency, even if it does not really work on a bigger scale than that what you can see here. The lower floor stands in a glazed atrium so that daylight can fall all the way down on 3 or 4 sides, southwest and north. The eastern side can be opened over a length of 10 meters by means of a large folding lift gates. Thus, even large objects can be brought in without any problems. The room behind, with a size of approximately 160 square meters, can be used as a workshop, as a studio, or as an exhibition space. On the northern side, there are adjoining rooms and the open technical center where technical building components are tested and replaced. Barrier-free access is ensured via the ramp to the east and north. A view into the studio space with a floor-to-ceiling wooden wall on the west side. On the left, the cross-out of the steel skeleton construction can be seen, with a non-sliding glazing in front of it. The pane in front of the wooden wall, on the other side, can be shifted 100% to the right. Thus, the ornamentation of the wooden stacks becomes a picture in the room. The ground floor is designed as a large, contiguous space. Only a utility block of lightweight construction with a check room and a guest toilet divides the space between the entrance on the northwest side and the room facing south to the garden. In front of the open windows are 3 exits covered with stone slabs, at different depths depending on their orientation to the sun. Between them, horizontal slabs of wood are stretched that, on the one hand, allow a walkable entrance, and on the other, bring daylight to the floors below. This zone between the thermal cover and the outer edge of the building is one of the main research and experimentation areas around the building. The spatial impression of the open kitchen facing south, on the right, the room divider with a darkroom height glass door for the kitchen cabinets behind. The iPad mounted in the wall is used for building control. In order not to disturb the open space impression, a hanging fireplace from Gyro-Focus was installed. The combustion chamber is rotatable so that the flame can be seen from the kitchen and the dining table. The wooden slats in front of the non-opening panes on the right and the stone slabs in front of the sliding elements on the left are clearly visible here. These panes can be pushed completely in front of the pane with a crossover, turning an entire wall of the room into an open exit. The floor is a color-darkened industrial floor with no joints or transitions to the floor-to-ceiling profiles. The guest toilet on the ground floor uses a living moss grass wall. This positively changed the moisture content in this small space, giving the impression of being outdoors. Control components such as faucets or soap dispensers are separated in the light gap on the left, so the water supply from Vola does not require faucets. The upper floor shows the characteristic grid of 5 by 5 meter room sections. 6 rooms are arranged cross-like. By means of simple lightweight walls, areas can be separated and connected or isolated by the integrated sliding doors. The same geometry order of the 3 exits and slats areas can be found here as well. It is also easy to see that each room can be accessed through 2 openings, which is important if the rooms are ever changed into smaller units. The southwest corner room with the stone elements and the wooden louvers in front of the sliding pane. Due to the textile stretched in front, there is no need to fall protection, as you can't fall through the room height textile. The bathroom on the upper floor with a shower and a sink in front of the moss grass wall, which makes a positive contribution to the indoor climate here as well. The passage doors along the facade, the second access logic of the rooms, are built of translucent glass and are room high. The textile skin must answer the following questions. How are strong fluctuations in the external climate detected and processed? How are solar radiation, light intensity, air temperature, air humidity, precipitation or wind detected? How can such a skin take into account location-specific environmental influences? It is conceivable that sound emissions, environmental stress, mechanical stress can also be detected. How can the location of the users in the room be localized within the geometry of the room? How are the number of users, the type of use, and the users themselves defined? Can an individual control be superimposed on the automatic control? What ability of individual override do we already have? How can the user adjust the visual reference to the outside or the private-public demarcation or the comfort level? How can these dynamic processes, which sometimes work diametrically against each other and take on completely different tasks at different points in the building, be achieved with one material, with one sensor, with one design idea? You can see now a number of concepts that are being used in the REALLAB from this research field of adaptive building covers at my chair of building technology at the RWTH in Aachen. We distinguish 4 groups of adaptive materials and functions: thermosensitivity, fluidity, self-reacting organic materials, and magnetic modes of action. In the following, I would like to introduce just 2 of them in more detail. The idea of the glyphosate is based on the linear openings within a pre-tensioned textile structure, which is intended to regulate the incidence of light through its degree of opening. The textile used is lycra, a fabric based on an elastan and polyurethane, with a very high stretchability, which also has a very low moisture absorbing property. It is also dimensionally stable, lightweight, and dyeable. Perpendicular to the vertical incisions, 2-way FGL wires are woven, which are thermosensitive to the external influences. In the open cool state, the wires have a circular structure and thus expand the textile outwards. Due to the deformation, they can generate large openings in 3-dimensional space. As the heat rises, the wire deforms into a linear structure, closing the facade pane to approximately 100%. The thermosensitivity here should lie in a spectrum of about 40 to 80 degrees Celsius. The advantages of the concept lay mainly in the properties of the FGL materials. Due to the adaptability of the thermoactors, the FGL wires can be adapted to almost any temperature range from 15 to 120 degrees. Thus, one could create different levels of permeability. In addition, the color spectra of the lycra fiber are adaptable to the building in question. In addition, the textile can be nearly stretched in front of the facade, and no additional spaces are needed to hide facade components. Thus, the facade would be understood as a uniform skin that is not interrupted. The developed facade, the second example, is based on the functional principle of chromatophore cells. Chromatophores are pigment cells that can be found, for example, in the skin of cephalopods, such as a squid. Muscle contraction causes an expansion of the pigment located in the center of the cell. The muscle contraction can be mimicked by using electroactive polymers, in this case, a dielectric elastomer. The basis for the systems was thus not a textile, but a highly elastic plastic. In this case, the elastomer was pre-stressed to 300% on an acrylic frame. A conductive graphite paste was then applied. The design of the conductive surface is completely optional. It's only necessary to ensure that the same shape is also applied to the back of the elastomer. The conductive surfaces were then connected with a copper strip, which in turn was connected to a voltage source. The dielectric elastomer represents the radially arranged muscles of the chromatophores. The coating of conductive graphite paste simulates the pigment sac of the cell. By biasing the elastomer, it can be considered as a capacitor. In a closed circuit, the conductive coat coated parts charge. Then voltage flows through the electrodes. The elastomers compress due to electrostatic pressure and thus expanded. The conductive surface also expands in the process. Since the graphite surface responds directly to voltage changes, the darkening effect occurs immediately. Furthermore, the expansion of the point is related to the strength of the connected voltage, so that there are not only the states open and closed, but also states in between. So by calling the points, it would be possible to reduce the necessary voltage. The unrestricted design of the second building shell is the greatest advantage of this system. It would be quite possible to make the individual points denser or larger in areas that are more private than in less private spaces. In addition to the freely designed space, color variations may also be possible. Coating the elastomer with, for example, textiles would lead to reduction of weathering by various environmental influences. By waving conductive threads into the textile, the connection path from every point to point would be less dominant. In addition, PV elements could be incorporated directly into the facade to ensure full adaptivity. Now see the living space with full transparency without a textile. Now see the living space with full transparency without a textile on the outside of the building. And now with a textile. It is astonishing that although we perceive a slight darkening, we do not feel that the view is disturbed. The textile on the outside. From the outside, however, a completely different picture emerges. The building without a textile and now with a textile. The textile on the outside must be able to change its opacity to allow both similar control and privacy in glazed rooms. In order to understand how our brain-eye combination deals with visual impressions, an investigation was undertaken in cooperation with the eye clinic of the University Hospital of the RWTH University in Aachen, with test persons who were asked to decode a sequence of partially encoded images. The intention was to find out what the human eye actually still perceives as disturbing before it composes the image of the observation on its own. This was to define the minimum value of flow that defines a quasi-free, undisturbed view through the textile. From left to right, with membrane completely closed, there is a clear separation between interior and exterior space. Light intensity, light incidence, and differentiated color spectra are perceived as a function of varying contrast intensity. The brain tries to assemble fragmented image information into a mosaic-like picture. Thereby, a comparison with known images and natural regularities takes place. Now the brain has enough information to recognize the fragmented image in an overall context and to assemble it like a mosaic. An intermediate level of detail recognition sets in. As the distance of the observer to the membrane increases, the membrane acts as a veil from the interior space, clouding the image of the exterior space in the color of the membrane components. The membrane components predominate and are perceived as a disturbance. The exterior space dominates over the membrane components. The exterior space is clearly perceived. A high level of deep detail recognition is presented. The membrane is perceived as less disturbing and the image clouding is less intense. The exterior space is clearly perceived with all detailed information. The membrane component dissolves almost completely. The image clouding stops. In this project, we were able to determine the following results using the 4 measurement protocols after 22 investigations over 4 years. The U value slightly increased, a consequence of poorly installed glazing, which leads to repeated condensation problems at the corner joints. The use of renewable energies is unchanged at 97%. More is currently not possible if you balance these calculations. The energy consumption is 5 points lower, which is mainly due to the optimized user behavior. As expected, CO2 savings are very high. The plot ends with the western courtyard towards the street, which is roughly 75 meters long structure. Situated directly by the moat, the finishing volume develops here for the restoration of the historical palace garden. Above House A, the palace, alongside the Four Fingers, building B and C, which are constructed in the 90s, as well as the old gatehouse as building D. Both the long rectangulars in the side plan depict the tree-lined avenue and a bordered field of grass, which once displayed a bed of roses. The new building underneath the palace will be developed on the left side, above a historical bridge, which used to lead across the water-filled moat. Today, the moat is a pleasant meadow. Its shape evoking its former usage as a protective structure. To the north of the new building, you will recognize the areaway with a flight of stairs for outdoor lectures. To the south is the delivery area of the building, which is connected to the road network via the withdrawn basement level. In this way, the delivery area is conveniently situated and somewhat apart, preventing excessive disruption of the teaching program. On the left roof is the roughly 420 meters PV energy field and the integrated skylight over the study areas along the eastern facade. The red rectangles are all around the new building, depict the installation areas for the local fire brigade. The view to the west from the courtyards shows the plot in its full length. You can almost touch the fixtures of both the layered stone volumes, which are separated by the glass interstices of the ground floor. Tranquil and constant, the building occupies the premises without any fuss, oozing serenity and aplomb. The souterrain volume is raised approximately 1.5 meters from ground level, so that the laboratories, which do not require any direct sunlight, still receive natural lighting and are connected to the ventilation systems to the outside air at the same time. To the left of the picture is the delivery area alongside the turf of the moat and the southern access point, which also facilitates barrier-free site development. The ramp for that is integrated nearly into the structure, and thanks to its slightly inclining geometry, it does not disturb the overall structure. The glazed ground floor between the stone volumes is set back, resulting in interesting overhang, which offer not only protection from the rain, but also offer their own special quality. The 4 floor plans on the side plan are, starting from the left, the basement level for the laboratories, the ground floor for professors and staff, the upper floor with the seminar rooms and the roof plan. The layout is consistent and rigidly efficient, structured with a 5-meter grid across the longitudinal direction and a simple 8.5-meter grid in the transverse direction. 2 core zones with unconcealed exposed concrete steps, supply ducts and a freight elevator are deliberately kept to a minimum. These areas must be robust and resilient, enough for usage by many people in this building. Behind the stairs are two restroom areas, one for women and one for men, which are arranged in such a way as to be efficient and easy to find again. The laboratories have differing sizes, but can be adjusted in the longitudinal direction according to the demand for teaching. The large room to the north is the aforementioned multi-purpose room with a free time area in front of it, which caters to the musicals and physical education of students. The glass ground floor, which is with its two cores, offers space for lectures and the management, as well as work and overnight rooms for external lecturers and researchers who only stay in the building on certain days. From here, one can step out of any room and find oneself under the overhang, offering protection from the rain, above the ground floor, from which emanate several rooms in which one may wish to linger. The upper floor offers 6 large seminar rooms, 2 core areas with restroom facilities, and a roughly 75-meter long study alcove along the eastern facade, offering a view to the courtyard. In the foreground is the historical bridge, which is connected to the courtyard and the new building. The overhang to the right of the picture offers external lecturers a canopied outer area and furthers communication with students coming and going from this part of the building. The rather flat stairs on the overhang inside the entrance over the old bridge into the building are cut into the pedestal and separate the students' direction of movement, as if by chance into south and north under the protruding upper floor. The glass interstices thus become a movement zone in which interaction should take place, both with the lecturers and between one and another. On the northern, narrow side of the plan, the open plan, free area of the multipurpose room edges upwards from below, crossing over an area with stairs for sitting and walking across. This area, a form of amphitheater beneath the beautiful trees, is a stage, auditorium, and free time area, all rolled into one. The canopied area on the ground floor becomes a gallery, allowing attendance from above at lectures and presentations. On the southern side, the arrangement of trees is much denser and offers shade, and becomes an open area in front of the professor's rooms, where you can debate, do's off outside, or simply spend some time for lunch. The slightly raised positions of this terrace area appears wonderfully well established in the old park, which one can easily look down upon from above. Seen from the main development area of the courtyard, the new building sits confidently in the park, yet, despite its size, it appears pleasantly withdrawn and conveys the sense of clear shapes into natural surroundings, cultivated over hundreds of years, the result of a specially employed architectural contrast. The same goes for the north side, with the multipurpose room and outer stairs sets inside it. The light-colored stone volumes play with proportion and width. Crucial to the elegant and well-proportioned shape are the 2 light-colored stone bars on the left and right, which amplify the vertical shapes in the surrounding area. The sailors amongst you will know that length matters. Now and then, the same applies to architecture. From the longitudinal perspectives, one appreciates the clear 5-meter grid pattern and the 3 floors, the cut of the stairs, the outdoor stairs and the entrances. The varying floor heights result from differing applications, such as 5-meter high lavatories, 3.5-meter high glass offices, and 4.5-meter high seminar rooms. The elevation fails neatly into categories and with a clear design language of large, coherent elements. Looking at the facade section in detail, the points to appreciate are the short passages on the floor and the roof, as well as the room-high superior stone laminations made from carbon concrete. These industrially produced components stand out for their immense precision and exactness, their cheapness to produce, and for being considerably lighter than conventional concrete. The roofs in the seminar rooms are cooled by concrete heating, and the floors are used as heat transfer surface. The room-high slabs, affixed to covered sections only, are triple glazed and thanks to the laminations stewed in front of them, require no additional protection from the sun. The entire energy concept is based on the usage of renewable energies. A geothermal field delivers preheat warm water for approximately 16 degrees Celsius to the heat pumps, which produce warm water of 38 degrees Celsius and heat the building in winter. In the summer, clean water from the geothermal field is funneled through the huge exposed concrete roofs and used to constantly cool the structure. Naturally, the exterior sun protection contributes to this considerably. The simulations for that large project are as follows. An average U value of 0.32, 68% use of renewable energies, an energy consumption of only 44 kilowatt hours per square meter a year, and around 165 tons of CO2 savings. We are talking about a modern all-electricity building without any fossil fuels. Everything is generated, saved, and used in accordance with local requirements. That is the lived future, and I hope that these values will also be confirmed in operation over the next years.